Hello everyone. In the previous class I have explained how to solve a non-homogeneous differential equation of type 1 and type 2 functions, that is exponential and trigonometric functions. In today's video I am going to explain how to find a solution of non-homogeneous differential equation if phi of x is a polynomial equation. For that I am considering a second order differential equation. Here phi of x is a polynomial equation. Solution of a differential equation is yc plus yp. In the previous video I have already explained how to find a complementary function. Now to find a particular integral if phi of x is a polynomial, so here is the procedure for that. Yp is equal to phi of x, that polynomial equation, divided by f of d, where f of d is the differential operator function. To get a particular integral in if phi of x is a polynomial, we have to divide that phi of x by f of d by writing phi of x as descending powers of x and f of d as ascending powers of d. We have to write these functions as phi of x as descending powers of x and f of d as ascending powers of d. So after writing that, we have to divide both the equations till we get a zero remainder. Till we get a no remainder or a zero remainder, we have to continue the division. After division gets completed, then the remaining quotient, the resultant quotient, is called the yp, that is particular integral value of a polynomial equation. For that, I will consider an example: 2x squared plus 4x plus 1 divided by d squared plus 3d plus 2. As I already told, we have to write phi of x in descending powers of x, that is 2x squared plus 4x plus 1, and ascending powers of d, that means we have to write the constant element as the first one. Here the degree of d is 0, d power of 0. Next term 3d plus d square. We have to write the numerator in descending powers of x and we have to write the denominator in ascending powers of d. Now we have to divide this equation till we get a zero remainder. So now we have to divide 2x squared plus 4x plus 1 by 2 plus 3d plus d square. So till we get a zero remainder, we have to divide this equation. For the first term, we have 2x square here and we have 2. To write the first quotient element, divide the first element by the first term here, that is 2x square divided by 2. Divide the first element from the first divider, that is 2. Here the value of 2 get cancelled, then the remaining element is x square. That means the first quotient is x. On multiplying x square with each element here, we get the resultant term, that is 2 into x square, that is 2x square, plus 3 into differentiation of x square, that is 3 into differentiation of x square. So 3 into differentiation of x square is 3 into differentiation of x square is 2x. Resultant term is 6x plus 6x plus next term is d square of x square. Next term is d square of x square. Differentiating x square twice, we get, differentiating once we get 2x, differentiating one more time we get 2 into 1, that is 2. Hence the last element is 2. Now we have to subtract these two equations by changing the sign. Plus 2x square minus 2x square get cancelled. Plus 4x minus 6x equal to minus 2x. Plus 4x minus 6x equal to minus 2x, and the value of 1 minus 2 equal to minus 2. till to 0 remainder we have to continue the procedure. Here we have minus 2x minus 1, that means we have to divide further. Again here we have the first divider 2 and the first element is minus 2x. Dividing minus 2x by 2 get cancelled. The next quotient element is minus x. Then multiply by with each element 2 into minus x minus 2x plus into minus 3 into differentiation of x. Differentiation of x is 1. 3 times of d into minus x, that is 3 into minus 1, we get minus 3. Next we have d square here. D square of x, differentiating once we get 1 and differentiation of 1 is 0, that means the next element is 0. Since this is a constant term, and differentiating one more time we get next element as 0. So that's why again changing the sign here, plus 2x minus 2x get cancelled, minus 1 plus 3 is equal to plus 2. Again we have 2 here, here also we have 2. To get the next quotient, to get 0 remainder here, 2 divided by the divider, first element of the divider 2. So 2 by 2 equal to 1. The quotient element is 1. 2 into 1 equal to 2. Differentiation of 1, since 1 is a constant term, on differentiating we get 0, that means the remaining elements are 0. On changing sign and subtracting 2 minus 2 is equal to 0. So here we have 0 remainder, that means the procedure completed here. To find particular integral for a polynomial equation, we have to divide phi of x by f of d by writing phi of x in descending powers of x and ascending powers of d. Till we get a 0 remainder, we have to divide the equation. Then the resultant quotient x square minus x plus 1 is called particular integral. That is yp is equal to x square minus x plus 1 is called particular integral. So this is the procedure to solve particular integral if phi of x is a polynomial equation. So let us solve some problems on this. On type 3, that is if phi of x is a polynomial, y double dash plus 3y dash plus 2y is equal to 12x square. Here 12x square is the polynomial. So let us find the solution of this. So this y double dash can be written as d square plus 3 times of d plus 2 times of y is equal to 12x square. Here this d operator, that is differential operator, is called f of d function. Phi of x is a polynomial, that is 12x square. So first find the complementary function, that is solution of the LHS part of the equation. For that, auxiliary equation is m squared plus 3m plus 2 equal to 0. M square plus 3m plus 2 is a quadratic equation. On factorizing this, m square plus 2m plus 1m plus 2 equal to 0. Here we have 3 and 2. So we have to select two factors such that on adding we get 3 and on multiplying we get 2. So that is m square plus 2m plus 1m plus 2. In the first two element, common term is m. Remaining is m plus 2. In the next two, 1 is the common element, remaining m plus 2. Simplifying this, again m plus 2 is the common factor, m plus 1 equal to 0. Simplifying this again, m plus 2 equal to 0, m plus 1 equal to 0. Hence m is equal to minus 2 comma minus 1 are the roots. So minus 1 and minus 2 are the real and distinct roots. Therefore, the complementary function is equal to, for distinct root, c1 e to the power of minus 1x, c2 e to the power of minus 2x is the complementary function. Next, to find particular integral, that is yp is equal to phi of x divided by f of d. We have to divide phi of x by f of d by writing phi of x as in descending powers of x and f of d as ascending powers of d. But for phi of x we have only single element, that is 12x square divided by writing f of d in ascending powers of d, we get 2 plus 3d plus d square. 2 plus 3d plus d square. On dividing this, x square, so we have to divide the 12x square by this differential operator equation by writing in ascending powers of d. And the first factor is 2 plus 3d plus d square. So we have to divide 12x square by this 2 plus 3d plus d square. To write the first, till we get a 0 remainder, we have to divide this equation. For that, first coefficient is, to write the coefficient, each coefficient value, we have to divide the first element of the dividend by the first element of the divider, that is 12x square by 2. 12x square divided by 2, which is equal to 6x square. The first quotient element is 6x square. Now multiply 6x square with all these elements. First element 2 into 6x square, we get 12x square plus 3d into 6x square. 3 into 6 is equal to 18. Differentiation of x square is equal to 2x, which results in 36x. So next element is 36x. This is how to find the quotient element, applying each factor, that is the first term. Next term, d square of 6x square. Writing the 6 constant as it is, differentiating once, differentiation of x square is 2x, 6 2s are 12, differentiation of x is 1. So the next element is 12 into 1, that is 12. On simplifying this, plus 12x square minus 12x square get cancelled, we left with minus 36x minus 12. We left with minus 36x minus 12. So next, to get the next quotient element, again divide the first element by the first element, that is minus 36x divided by 2. We get minus 18x. So next quotient element is minus 18x. Simplifying again, 2 into minus 18x, that is minus 36x. Next term, 3d into minus 18x. Simplifying this, 3 into minus 18 is minus 54 and differentiation of x is 1. So here we have x to the power of 1. On differentiating once, we get 1. Here we have d square. If we differentiate this element twice, we get 0, because on differentiating 1 we get a constant term. Differentiating one more time, since it is a constant term, we get next element as 0. So here we get minus 54. On simplifying this, and the last term is 0 here, plus minus 36x plus 36x get cancelled. Next term, 54 minus 12. 54 minus 12 is 42. So the next remainder is 42. But we have to continue the procedure till we get a 0 remainder. Since we have 42, to write the next quotient, 42 divided by 2. 42 divided by the first element. On simplifying we get 21. So that is plus 21. 2 into 21 is equal to 42, and multiplying the next term, differentiation of 22, so 21. Since 21 is a constant term, it is equal to 0. So the last term is 42. Simplifying this, minus plus 42 minus 42 get cancelled. We get a 0 remainder. So therefore the remaining quotient will be the particular integral. So here particular integral value is dividing 12x square by the differential operator equation, that is what we get, 6x square minus 18x plus 21. This is the particular integral. Therefore solution of given differential equation is y is equal to yc plus yp, that is y is equal to, what is yc? c1 e power of minus x plus c2 e power of minus 2x, and yp is equal to 6x square minus 18x plus 21 is the resultant solution of the given differential equation, that is complementary function and the particular integral. Next problem in type 3, solve d cube x by dt cube plus 3d square x by dt square, which is equal to 1 plus t. Here the given equation contains x as dependent variable and t as independent variable. For this, to write the solution of this differential equation, we have to write x in terms of t, that is x as a function of t. While solving the differential equation, the solution is we have to write the value of the dependent variable in terms of the independent variable. Here the dependent variable is x, hence we have to write the solution x as a function of t. So remaining procedures are same. First find the complementary function of the given equation. Let us take the given differential equation in differential operator form, d cube plus 3d square of t. Since here independent variable is equal to t is equal to 1 plus t, which is the given polynomial equation. To find the complementary function, auxiliary equation is m cube plus 3 times of m square is equal to 0. To find the roots of this auxiliary equation, we can easily factorize this because m square is common in the both element. By taking m square as a common term, remaining element is m plus 3 equal to 0. Simplifying this, m square equal to 0 and m plus 3 equal to 0. M square equal to 0 is nothing but m is equal to 0 comma 0 and m is equal to minus 3. Therefore the complete roots are m is equal to 0, 0, minus 3. Here in the first two, the roots are real and coincident here. We have 3 roots here. One root is real and distinct and 2 roots are real and distinct. Therefore, we have to write the solution in terms of x as a function of t because x and t are the variables here. Therefore, complementary function is xc here, that is x in terms of t is equal to c1 plus c2t into e to the power of 0t plus c3 into e to the power of minus 3t. That is the last distinct root. This is the complementary function. Next, to find particular integral. Next, to find particular integral xp. So if the given differential equation contains dy by dx as a derivative, the complementary function and particular integral are yc and yp. Since the given equation is in terms of dx by dt, complementary function is xc, particular integral as xp, we have to divide phi of t divided by f of d. To divide these two and to get a particular integral, we have to write phi of t as descending powers of t. So descending powers means first we have to write t power 1 and constant term, that is t to the power of 0, divided by ascending powers of d. Ascending powers of d means first we have to write 3 times of d square plus d cube. So we have to divide this to get a particular integral. So to divide that, we have to write numerator as descending powers, denominator as ascending power, that is 3d square plus d cube. Till a 0 remainder, we have to divide the equation here. T plus 1 we have and 3d square plus d cube we have here. To get a first quotient, we have to divide the first element by the first element. So what we get? T divided by 3d square. T divided by 3d square. Here 1 by 3 is the constant term. 1 by d is nothing but integration. 1 by d is nothing but integration. If we have 1 by d square, we have to integrate twice. That means t by 3d square is 1 by 3 into double integration of t. So that is 1 by 3 into integrating once, we get t square divided by 2. Integrating once, we get t square by 2. Integrating one more time, 3 into 2 6. Integration of t square is t cube divided by 3. So the resultant term is t cube divided by 18. Hence the first quotient element is t cube divided by 18. Then 3d square into t cube by 18 is t. So here we are dividing the same term, that is 3d square into t cube by 18 is equal to t plus d cube into t cube divided by 18. Differentiating once, that is d square, differentiating once we get 3t square by 18. 3 ones are 3, 6 are. Differentiating one more time, 2t divided by 6. Again simplifying this, we get t by 3. Differentiating one more time, we get t by 3 derivative is 1 divided by 3. Differentiating t cube by 18, 3 times we get 1 divided by 3. Simplifying this, plus t minus t get cancelled and 1 minus 1 by 3. So 1 minus 1 by 3 value is 2 divided by 3. 1 minus 1 by 3 value is 2 divided by 3. Next, to get the next quotient element, we have 2 by 3 here and we have to divide this 2 by 3 by 3d square. That is 2 by 3 divided by 3 times of t square. Simplifying this, 2 divided by 3 into 3 9, 1 divided by d square. 1 over d square is nothing but 2 by 9 double integration of 1. In the numerator we have 1 here. So integrating that, 2 divided by 9, integrating once, integration of 1 is t. Integrating one more time, 2 divided by 9, integration of t is t square divided by 2. Here the value of 2 get cancelled. The resultant element is plus t square divided by 9. So the next quotient is t square by 9. Multiplying with the factors, 3d square of t square by 9 is equal to, here 3 1s are 3 3s are, 1 by 3 is the constant term. Differentiating once, d of differentiation of t square is 2t. Differentiating one more time, 1 by 3 differentiation of 2t is, we get 2. So the differentiating twice into 3 is equal to t square by 9 is 2 divided by 3. On differentiating twice, we get a constant term here. Here we have to differentiate 3 times. Differentiating twice, we get a constant term. On differentiating 3 times, we get 0 here. Since this is a constant term, the next element is 0. On simplifying this, plus 2 by 3 minus 2 by 3 get cancelled and the remainder value is equal to 0. Hence, the particular integral value is the obtained quotient term, that is xp is equal to t cube divided by 18 plus t square divided by 9. T cube by 18 plus t square by 9. Therefore, complete solution of given differential equation is x is equal to xc plus xp. X is equal to xc value is c1 plus c2 into t, and the value of e power of 0t is equal to 1, remaining c3 plus e power of minus 3t plus particular integral value is t cube by 18 plus t square by 9. T cube by 18 plus t square by 9. So this is the solution of the given differential equation. Next problem on type 3, that is if phi of x is a polynomial, is y double dash plus 2y dash plus y is equal to 2x plus x square. So the given polynomial is 2x plus x square. To find the solution of this, first we have to find the complementary function using the LHS part and particular integral using the RHS part. So the given equation is y double dash plus 2y dash plus y is equal to 2x plus x square. Let us write this equation in differential operator form, that is d square plus 2d plus 1 of y is equal to 2x plus x square. To find the complementary function of this equation, let us write auxiliary equation by replacing the differential operator to a constant term m, that is m square plus 2m plus 1 is equal to 0. So the equation is m square plus 2m plus 1. So here no need to factorize this because this is in the standard form, a square plus 2ab plus b square, where a is equal to m, b is equal to 1, which is equal to m plus 1 whole square. So that is m plus 1 equal to 0, m plus 1 equal to 0, m is equal to minus 1 comma minus 1 are the obtained roots. So the roots are real and coincident here. The real and equal roots we have. Therefore, complementary function, that is yc is equal to c1 plus c2x into e to the power of minus x. Complementary function is the first part, c1 plus c2x into e to the power of minus x. Next we have to find particular integral, that is to find yp value. Formula is yp is equal to phi of x divided by f of d. Phi of x divided by f of d. To divide this phi of x by f of d, to find the yp value, if phi of x is a polynomial, we have to write the numerator, that is x function or phi of x in descending powers of x, and we have to write f of d as ascending powers of d. The descending powers of x is, here the given equation function is 2x plus x square. Writing this in the descending powers of x, first element is x square, second element is 2x, and in the denominator f of d, we have to write f of d in ascending powers of d. So the first element is 1, increasing powers of d, first element is 1, 2d, d square, 1 plus 2d plus d square. To find a particular integral if phi of x is a polynomial, after writing the formula phi of x by f of d, we have to divide phi of x by f of d by writing phi of x in descending powers of d and f of d as ascending powers of d. Numerator as descending powers of x and denominator as ascending powers of d. So let us divide that equations. We have x square plus 2x and divide by 1 plus 2d plus d square. We have to divide these two equations till we get a 0 remainder. After getting 0 as a remainder, then the resultant quotient will be the particular integral value. To find the first quotient element, as I already explained, we have to divide the first element of the dividend by the divider, that is x square by 1. X square by divide by first element, x square by 1 equal to x square. Then the first quotient element is x square, that is 1 into x square is x square plus 2d of x square, 2d of x square, that is 2 times of differentiation of x square. Differentiation of x square is equal to 2x. So the resultant element is 4x. Second element is 4x here. Next term d square into x square. Next element d square into x square. Differentiate twice. Differentiate x square twice with respect to x. Differentiating once we get d of 2x. Differentiation of x square is 2x. Differentiating one more time we get 2. So differentiation of x square twice is equal to 2. So the next term is equal to 2. So simplify this by changing the sign, minus, minus, minus. Here the value of plus x square minus x square get cancelled. Plus 2x minus 4x equal to minus 2x minus 2. Next we have to find the next quotient element. Again divide the first element by the first element. We have, so we have the first step completed. Next step, minus 2x divided by 1. So that is minus 2x. Since we have 1 as a first element in this term, we get the same element as the quotient. So that is 1 into minus 2x minus 2x, 2 into differentiation of minus 2x, 2 into differentiation of minus 2x. Here x power is equal to 1. On differentiating once we get a constant term. 2 times of minus 2 is a constant term. Differentiation of x equal to 1. The resultant term is minus 4. And in the next term we have d square. After differentiating once we get a constant term here. That means differentiating one more time, that is differentiating twice, we get 0 because differentiation of a constant term is 0. That is we get 2d of minus 2x as minus 4. Differentiating twice the same element equal to 0. Since on differentiating once we get a constant term. So the next element is minus 4. Simplifying this again, plus minus 2x plus 2x get cancelled. The resultant term is equal to plus 2. Minus 2 plus 4 equal to 2. Again divide this element by 1. 2 by 1 is equal to 2. So then 1 into 2 is equal to 2. Next 2d of d. 2 is a constant term. Differentiating that constant term we get 0. Hence the remaining elements are 0. Simplifying this by taking negative sign, plus 2 minus 2 get cancelled. We get a 0 remainder. We have to divide phi of x and f of t till we get a 0 remainder. So here we obtain 0 as a remainder. Then the resultant quotient will be the particular integral value, that is x square minus 2x plus 2 is the particular integral value. X square minus 2x plus 2 is the particular integral value. Therefore final solution and complete solution is y is equal to yc plus yp. Y is equal to yc value is c1 plus c2x into e to the power of minus x, and particular integral value is x square minus 2x plus 2. So this is the solution of given differential equation if phi of x is a polynomial function.